Hello, ladies and gentlemen, and welcome back to question number 4, question 4 out of 10, on our 2009 Euclid paper. Okay, so what have we got for question number 4? It's a two-parter. Again, light bulb and written. This tends to be the pattern for the middle questions. First two questions are often 3 parts, and then everything through till about 7 is usually 2 parts, light bulb, written, and then the last 3 questions are just a series of written. Usually. Not always, but usually. Alright, so 4a, in an arithmetic sequence, the first term is 1 and the last term is 19. The sum of all the terms in the sequence is 70. How many terms does the sequence have? And in case you don't know what an arithmetic sequence is, they are nice enough to provide this for you. They'll do that for arithmetic sequences and geometric sequences and a couple other math concepts that should be common but have slowly been phased out of things like the curriculum. So an arithmetic sequence, just you get the next term by adding the same number to the previous term. So we get to 5 from 3 by adding 2. That's how we get from 5 to 7, and then 7 to 9. Just keep adding 2. Alright, so first term is 1, last term is 19. Okay. I don't know how many terms. That's the challenge. We want to know how many terms my sequence has. I know I start with 1, and I go to 19. There could be 5 terms, there could be 6 terms, there could be 6 million terms in between. There probably aren't that many. Okay? But I might say something like, not common ratio, common difference tends to be what we call it. Okay? In general, an arithmetic sequence starts A, and then A plus D, and then you keep adding on D each time. Okay? So that tends to be how it goes. And then, if your nth term will be n minus 1D plus A. Okay? And you can get formulas, for example, we know 70 is the sum of the arithmetic sequence. If we add up n terms of an arithmetic sequence, the formula is NA plus n minus 1 over 2D. And this is nice, but I don't think this is a formula we're going to want to use. But it's something that's there. Try and prove it on your own if you're curious about that sort of thing. But I don't think I'm going to need that. What I can do is say, all right, then my sequence must look like 1 plus D up here. And then, well, how did I get to 19? Well, the previous term must have been 19 minus D. That way, when I add D, I get the term 19. And then I get 1 plus 2D, and then 19 minus 2D, and then, 1 plus 3D, and 19 minus 3D. And I'm running out of space, but we just keep going on in between this. Okay? We'll write this out. And so I can sort of work backwards and forwards. Now, how does this help me figure things out? Well, if I take a look at pairs here, I know what 1 plus 19 is. It's 20. But if I look at the next innermost pair, I get 20 as well. 20, 20, 20, 20. This is going to keep going. I'm just going to keep adding up pairs of 20. The only way I wouldn't add a pair of 20 is if, we had a middle number that, so we didn't sort of have a mirror image. But look here. So the 1 and the 19, they're part of what I have to add up. They give me a 20. The 1 plus D and the 19 minus D, they give me a 20. So now I'm at a total of 40. So rather than adding up, 1, 2, 3, 4, 5, and adding up that way, I'm adding pairs. Which, incidentally, is how you prove that formula NA plus n minus 1 over 2D. But we don't need that. So 20, 20, 20, that's 60. If I added on another 20, that would be 80, and that would be too much. So I guess I don't have that many terms, or these middle terms. So I don't need these. Okay? So just with 3 terms at the start, 3 terms at the end that are different, I get 20, 20, 20, and that's 60. But that's not enough. The sum they tell us is 70. 60, not 70. So we're missing a 10 in the middle. Okay. That's the amount. If I had two numbers in between these 6, then I'd get another 20, and that'd be too much. So it's got to be this leftover amount of 10. And so now I've got 1, 2, 3, 4, 5, 6, 7. So our final answer is 7 terms in our sequence. Okay. So I'd put 7 in the box. It was how many terms, right? Yeah, how many terms. Alright, so that's A part. We don't have to explain that a whole lot, but, I would draw maybe that little picture with the 20s adding up. And then, for B, this is the written one. Suppose that A times x plus B times x plus 3 is equal to 2x plus 6 for all values of x. Determine A and B. Okay, so I'm going to write this as 2x plus 6. A, it was x plus B, and I want to say it was x plus 3, or was it minus 3? I can't remember. Nope, managed to figure that out and copy it properly. So over on this side, I'm going to get 2x plus 12. I might say, off on the side, expand out. Okay, so we'll get, ax plus ab, x plus 3. And then I'll get ax plus abx plus 3ab. So I'll get a plus ab, x plus 3ab. Alright, so this has to be the same as 12x, or 2x plus 12. Okay, so how am I going to do this? Well, both are polynomials. They're technically both lines. But for them to be equal for all x, the polynomials have this really, really nice property, and a lot of times we take it for granted, or we don't think about it, but we take it for granted that, if two polynomials are equal in the same amount of value, or on the exact same set of values, for all x's, then it turns out their coefficients must be equal. Okay, this is a really nice result. So, if 2x plus 12, there's not going to be another polynomial 3x plus 4 or something that does exactly what 2x plus 12 does. They can match sometimes, but to match for all x's, you have to have the coefficients match up perfectly. Okay? So, this is something that pops up every once in a while. It pops up in my second year calc course sometimes, and it pops up on contests every now and again. And as I say, we don't really think about it. We often take it for granted. But it should be mentioned here because we're about to use that result. Okay. So to be equal for all x's, the coefficients must be equal. So that tells me 2 is the same as a plus ab, and 12 is 3 times ab. So AB is going to be 12 over 3, which is 4. And then 2 is A plus 4. So A is negative 2, and B is 4 over A. So that's 4 over negative 2. It's also negative 2. So AB equals negative 2, negative 2. Okay? And if you want to, you can even double check. Negative 2 and a 4 here, and 4 times 3 is 12. 4 plus negative 2 is 2. So there we go. But probably circle that or put a box around that as a very clear final answer. But we didn't need to do a whole lot. It's question 4. It's not that intensive, but expand things out, collect like terms, group things together, and then we have to exploit this fact that for polynomials to be equal everywhere, their coefficients have to be equal. Okay? And from there, it all sort of falls into place. All right. So that's question number 4. Up next, of course, will be question number 5. Feel free to skip over to that video if you would like to. Feel free to leave a comment, throw a like on the video, subscribe if you want to be kept up to date. All those wonderful things show your support and let me know to keep going, but you don't have to do any of that, and you can just move right on to question number 5, or heck, you could move on to question number 9 if that's the next one you want to see. But whatever it is, I will see you guys in the next video for more Euclid.